So yeah, welcome everyone. Today I'm happy to have Alberto Ardid with me from the University of Canterbury in New Zealand. And he and his co-workers, they recently published a study in Nature Communications where they use transfer machine learning to help predicting or forecasting eruptions at volcanoes. And what's the very interesting aspect of their work is that they use data from well-monitored volcanoes and transfer it in some kind to less well-monitored volcanoes to help predicting the eruptions there. So now, before diving into your work, can you maybe give us a little status quo report on the use of machine learning in volcano research at this point in time? Is it already used at volcanoes, and to what extent, and how good is it? So can we already use it to predict eruptions in some kind of way?
Well, first of all, thanks for inviting me. Really exciting to be here with you and discussing this paper that we released like a month ago, I think. So in terms of the machine learning, it's definitely like a tool that is most of volcanoes observatories and people and research groups around the world are using. So, but AI tools, is a quite broad spectrum of different techniques. What I've seen that people is mostly using it for is typically for classification of volcanic signals like LPs or VTs or different type of signals that we have some understanding of what they mean because we have been observing it over decades now. So what typically are people doing is just that's a process that in the old days, volcanoes observatories have people onto it, classifying the type of signals for the different volcanoes. But now there are, several algorithms and a lot of people working on the problem of classifying this type of signals. On the other hand, the approach that we have been developed works is a classification problem, but it doesn't work by classifying standard volcanic signals, but it uses statistical tools to try to detect statistical patterns in the signals, in the oncoming signals that are similar to other patterns, statistical patterns that were observed before eruptions in the past, right? So it's pretty much, I'll say, it doesn't care about which type of signal is or if we understand it or not. It just looks for similarities in the statistic of the signals that I'm observing, for example, now, compared to the ones that I observed in the past, with the data that we train our machine learning models. And the key advantage there is that it gives you can transform that in a certain short-term probability of, how similar. So the question that the model is answering continuously is how similar is the new data compared to the one that I observed before eruptions in the past. And you can translate that into a certain likelihood or probability or some other ones, or a similarity of, or the likelihood of an eruption in the near future. So that's the key difference, I'll say.
Yeah. Okay. So, and I think you already started diving into your work a little bit, but now can you break down in simple words what transfer machine learning is? And then also when thinking about your work, can you tell us how did you train your model? So what data is in there? What volcanoes are in there? What types of eruptions are in there?
So basically, the transfer learning refers to this idea that you can use information from one system and transfer it to other to use, what you capture in some system to another one, right? So in terms of basically specifically to this paper, what the key idea that is behind the transfer learning is that we show that eruptions from, let's say, an initial group of volcano can learn to anticipate eruptions at other volcanoes that the model haven't seen before, right? Why is this important? Because you typically can train this type of models with volcanoes that have multiple eruptions recorded in the records, right? Key example for us is a volcano named Whakaari here in New Zealand that have over 10 years of that have erupted roughly 5 times over the last 10 years. All of them were recorded with, we have excellent records for it. So in that type of volcano, you can even just use information from that volcano. That's what we call a data-rich volcano in a sense, to train a machine learning model, right? But Whakaari and some other ones are kind of exceptions, I'll say, to the rule. Most of volcanoes, typically volcanoes erupt every 100 years, 1,000 years, or some of them haven't been erupted yet, right? So, and we have been recording seismic signals, which is the data that we use, which is this, basically sensors that record the vibrations in the surface of the volcano. We have been recording that type of signals over the last 2 or 3 decades. So we have really few records of eruptions in volcanoes, right? So Whakaari is an exception, for most of probably, potentially, that's 1% of the volcanoes that are monitored have, decent eruptive records to train their individual machine learning models. The idea that we are testing here is that let's use data in these data-rich environments, or let's train models in these data-rich environments like Whakaari or Copahue in Chile or Vesimiani in Kamchatka or some other ones. Train models using those and implement it in volcanoes that doesn't have enough eruptions to train their own models, right? Or you don't have enough records to even develop any type of forecasting model, right? So this key is this is the transfer learning part, which is basically saying that now we can implement this kind of models in not a few volcanoes, but hundreds and thousands of volcanoes now.
The next question or the next step of your work would obviously try to implement this approach in the short term or in the midterm at those volcanoes where we don't have the data because there are no eruptions or because there is not a dense monitoring network. So have you already tried to implement your approach at such volcanoes? And also, how feasible is it to implement it? So you said you need seismic data. Does this mean you need actually local seismic networks, or can you use global seismology data for this?
In this case, we typically don't work with catalogs or any kind of process seismic data. We just use the seismic data from, typically we use just one seismometer over, close to the volcano that we are monitoring, or hopefully close to the crater. We have a model running here in Whakaari volcano. Unfortunately, Whakaari have a big eruption on 2019 where 22 people died. And after that, nobody has been allowed to visit the island. So, and around 3 years ago, the seismometer there went down and haven't been replaced yet. And we have a current model, basically the model, what it does, once you train your model, you can just download from, online servers data that are being streamed in real time. And then you just process it through the model that you have trained in the past, and it will, for every time that you input some data, it will spit kind of a likelihood of a probability of an eruption in the next 2 or 3 days, right? So it's quite easy to implement. It's just like actually the model that we have for Whakaari is just it's a model that runs on the cloud. That is a Python loop in the cloud that basically downloads the data from the GeoNet, which is the monitoring group, the monitoring agency here in New Zealand. It processes the data, it runs it through the model already trained, and gives us an output that is printed in a web page that we and the monitoring agency have access to it, right? So that's what we have here in New Zealand. We are working on now. We are starting conversations with the observatory here to implement it for Ruapehu, which is a big volcano in the middle of the North Island of New Zealand. And I also have some collaborations running in other places, like in Chile, for example, in Italy too, and also with people from Singapore, on trying to implement this kind of monitoring tools in different observatories. However, I'll say like this paper is not exactly about, it doesn't say too much about the implementation. So what we are showing here is, the science behind it. But for the implementation, there is I'll say, the research from here is, is promising. I would like, to emphasize here that the model is still, you can say, this under development, and it required testing over different places. So and before implemented, or when implemented, you need to work closely with observatories and monitoring agencies to adapt the tool to their needs and ensure that is effectively implemented if it's going to be used for decision making, right? So that's a different step. Like, how do you calibrate the output of the model for the people that is going to use it so it's informative for their needs, right? Because, for example, it's different if you are monitoring a volcano, Ruapehu, that I mentioned in the middle of the North Island of New Zealand, where a lot of people live around, compared to a volcano that is, one of the Alaskan volcanoes that typically are monitored for air traffic purposes. So the level of exposure around each volcano, the level of tolerance or the risk tolerance that your implementation should have, right? So those kind of the questions that you need to work with the volcanoes observatories to implement these kind of tools. And by the way, I just remember that I missed one part of the last question, which was about the volcanoes that we are using. We are using in this study around 24 volcanoes from New Zealand, Japan, Alaska, Central and South America, one from the US, and aliens, and yeah, it's a kind of a decent representation of some of the volcanoes out there.
Yeah. Okay, cool. Well, this already sounds quite promising. So can you just give a brief outlook on what's next for you and your team? So what are the next steps to elaborate on this work and on this model? And also, can you give us a brief outlook? What do you think where AI or machine learning in terms of volcano eruption forecasting is bringing us in the next 5 years, let's say?
The next step for us is going to be trying to incorporate not only seismic data, but more data to it. I'm thinking, continuous gas emissions, any sort of observation around the volcano that can be recorded as a time series can be assimilated by these kind of models. Deformation data, for example. Then there is a big question, on the time length that each of these observations are recorded, but that's something that we have been working on, and for some months now. We are just trying to get the best multi-data set possible to test actually what it needs to be tested when you're working with data that is sampled at different frequencies, right? So that's a key challenge for us. That should be the next paradigm, like multi-data set. We are also working on implementation of these kind of models, asking those kind of risk tolerance and how this should be implemented in real time. And for the future, I think that I'm hoping that this kind of tool will be, accepted by the community, hopefully. And also we have in regard of this, we have another big line that we are developing now, which is, trying to make these kind of models as interpretable as possible, right? Using different techniques. We typically use, for example, in our models, random forest, and that's not a random decision. It's basically because random forests you can have access what part of the data are being used to inform the decision trees and in the random forest. So, and why it's important to be, when you're developing this model and for decision making, you need to think that the people is going to be using it are, volcanoes observatories that will be making decisions with it. So it's really important for them to understand actually what the model is doing, right? So we have received in the past a lot of criticism about, the black box nature of machine learning models, which is in a sense, I think is not the most important question, because the most important question is, if it works or not. That's actually what machine learning is about. It's about like figuring out if this kind of mathematical structures can do a better job that we can do for, using physics models or even our own intuition. But a secondary aspect for the people that is making decisions with it is, to understand what the model is doing. And it's pretty fair, because, if things doesn't work, they, can't blame machines, right? So
yeah,
they need to have some understanding of the model. So we have been working on developing, risk metrics derived from the output of our models that are more easily digestible by just common people, normal scientists that don't need to be expert in machine learning. And also in real time, how you can get information about what actually the model, why is predicting what is predicting, right?
Yeah.
And that requires a lot of work, and that's really exciting. And this is kind of the big challenges that I'll say, like in any field that machine learning is, they are facing it now, right? And in the next years, I think my feeling is that the volcanology community moves a bit slow compared to other fields, for whatever the reasons are. There are, pros and cons of that. But my expectation for the next 5 to 10 years is hopefully at least they will kind of assimilate to be part of their tools, this kind of studies or this kind of tool that we are developing, right? So
yeah,
actually the way that we imagine this kind of tool is just, an extra screen where they can, along with anything that they are doing, to complement it, to help it to make more informed and better decisions, right? So, but it's definitely, as in any field, there are people that is enthusiastic about it and people that is not so enthusiastic about it. And so, yeah, I think, but I'm positive about it.
Yeah. Okay, cool. Well, thank you very much for your time and for walking us through your work, and in particular through machine learning in volcanology, which is obviously a complex topic, but I think this was very insightful and you broke it down very well. So thanks for this.
Thank you so much for the invitation, and please, for anyone in the audience that want to share some thought with me or with us, just flip us an email and I'll be happy to. Or if you are thinking about collaboration, you have, for example, an exceptional multi-data set that we can use, we will be happy to if you get in touch.